And we had talks given mostly from the US, but we had a talk given from Denmark, we had a talk given from Canada. This happens to be a screenshot of what you were seeing when there was a speaker from Japan who happened to be speaking at 3 a.m. in the morning, because when you do a workshop like this live around the world, you discover that the Earth is definitely not flat. The sun comes in from different angles, and we have time zones. And when we do it for the daytime in one hemisphere, it's the middle of the night in the other hemisphere. There's not too many ways to get around that. Although we are planning to do one of these with Europe, in which we will choose a 4-hour window that works pretty much for everybody in Western Europe and works pretty much for everyone in the United States. And similarly, it would be very easy to do one between North America and South America, because we share time zones for the most part, so we wouldn't have so much problem here. So this is something that we can think about. So let me tell you a bit about astrobiology missions. The first mission I wanted to tell you about is Kepler. Kepler is a mission that launched in March of 2009, and it is in some ways a very, very simple astronomical mission, but a very, very difficult one to actually build. And it was a tremendous credit to the team that put this mission together. It is a wide-field telescope which has a single instrument, a photometer, which measures the brightness of stars, doesn't even break the light up into the spectrum. It measures the integrated light over several thousand angstroms. And it basically stares at one place in the sky and monitors the brightness of 100,000 stars for several years. 3.5 was the nominal mission. And what it's doing is it's looking for that tiny drop in light that occurs when a planet passes in front of a star. So here we see a planet, a remote planet, passing in front of a distant star. Of course, we can't resolve the star. We can't see this happening, but this is what's happening. What we do see is we measure the integrated brightness from the star, and as the planet moves in front of the star, that brightness decreases just because the planet's blocking out some of the light, and then it comes back up. So this is what Kepler is looking for. Now, of course, Kepler is optimized for Earth-sized planets, and in an Earth-sized planet, this drop is 1 part in 10,000. So you need very high signal-to-noise ratio, and then, of course, to confirm that this is really a planet, you need to see more than one of these drops. You need to see at least 3. That is, you see a drop, then you see another drop sometime later. Now you want to see a third drop the same time interval later, and only then will you say, I've got a planetary candidate. Even then, it might not be a planet, because just picture a double